All right, today we are going to take a look at the ideal gas law and stoichiometry together. So we're going to be using moles and balanced reactions to relate reactions involving gases and put that together with what we've learned with the ideal gas law. So make sure you have your calculator out. Also make sure you have a periodic table out in case you need to calculate any molar masses. So the ideal gas law and using moles. We are often concerned with finding the amounts of reactants or products in a chemical reaction, and many chemical reactions may involve gases. So the ideal gas law can be used to find the moles of a chemical in a reaction given pressure, volume, and temperature. So if we have our ideal gas law, we can find the moles of one of our chemicals. Mole ratios could then be used to apply the information from the ideal gas law to a chemical reaction and find out more information about it. If a reaction is done at STP, standard temperature and pressure, then we do not have to use the ideal gas law, and we can use 22.4 liters equal to 1 mole as our conversion. So that gives us kind of our shortcut. So we have kind of two options that we would first look at is if our situation is at STP, go ahead and do a straight stoichiometry problem. You can use the 22.4 liters to convert, and it's kind of stuff we've done before. If it is not at STP, and you will be given other temperatures and pressures, then we have to involve the ideal gas law. So that's our first thing we can look at and decide which path we're going to take in these problems. So a few things just to keep in mind when you're approaching stoichiometry problems. We always use our molar mass from our periodic table to convert between grams and moles of chemicals. So however many grams from the periodic table equal to 1 mole of that chemical. We use mole ratios to convert between chemicals in a reaction. So we get the information from the coefficients in the balanced reaction. And something you learned last year, kind of our mapping out of our problems. And I'll do an example of this as a reminder. It's our little trick that grams and liters on the roof, moles on the street to map out your problems if you need to. So we'll take a look at an example of that on the next slide. So taking a look at an example problem just to map it out as a reminder. Our example says if 3 grams of oxygen are reacted, how many liters of water will be produced at STP, standard temperature and pressure? So looking at our question, we can identify that we're given 3 grams of oxygen and we're looking for liters of water. So to set up our mapping, the first thing I do is I like to box the chemicals that I'm going to be using. So I'm using oxygen and water. Then we want to take a look at where we're starting. We're starting with oxygen and it's given in grams. And we're trying to find the water in liters. So grams and liters are on the roof if we think of these like our little houses. And everything else, all the moles are on the streets, like our little houses on the street. So first thing, if we want to get from grams to liters, we cannot jump from roof to roof. So first thing, we have to come out of our house down to the street. So we first go from grams and we convert to moles down on the street. So we go from grams of oxygen to moles of oxygen. Then we would want to go down our street to get to our water. So we would have to convert from moles of oxygen to moles of water. So that's the second conversion. Then finally, we would want to get to the unit that we want, which is liters. So we would have to convert from moles of water to liters of water. In this case, if we were to work out this problem, since it's at STP, we could use the 22.4 liters per mole and do that last conversion pretty straightforward. So that's just an example of kind of mapping out your question, seeing where you are and where you need to end up and how many conversions it takes to get there and what units you're converting between. If you never saw this last year and would like to see another example ever, kind of how to map out stoichiometry, come talk to me and be glad to help you out on that. All right, so we're going to take a look at doing these problems with a couple of examples. That's our best way to see how stoichiometry and the ideal gas law will fit together. So you have your first example on your paper. So auto airbags are inflated by nitrogen gas generated by the rapid decomposition of sodium azide, NaN3. So that first sentence is just describing our reaction. So you can see in the reaction we have solid NaN3, that's sodium azide, and when it breaks down or decomposes, we get sodium solid forming and we get nitrogen gas forming. So that gas is what's actually inflating airbags in a car. An airbag has a volume of 36.0 liters and is filled with nitrogen gas at 1.15 atmospheres and 26 degrees Celsius. How many grams of NaN3 must be decomposed to fill the airbag with nitrogen? So looking at this question, we're given quite a few things. We're given liters, atmospheres, and temperature. And it's good to note that all three of those are talking about, it's giving us that volume of the airbag, and it's talking about the pressure of the nitrogen and its temperature in the airbag. So once it's inflated. But the question that's asked is how many grams of the NaN3 have to be used to fill up that bag with nitrogen. So we're given both information about nitrogen and information about the NaN3. Or we're asked a question about the NaN3. So we're kind of dealing with two different chemicals. Whenever we're dealing with two different chemicals, that's your clue that you have to use some sort of stoichiometry in the question, because you're going to have to convert from one chemical to the other using that mole ratio. So we're going to take a look at how to solve this on the next slide. All right, so to solve this question, the first thing we should do is pull out all the important information out of our question. So the first thing is that we know we want to solve 4 grams of NaN3. That's our big question. And then we want to figure out what all we're given. So we're given a bunch of variables, and they're all talking about nitrogen gas. We're given that pressure, volume, and temperature. So let's go ahead and record our variables for our ideal gas law, since that's our situation that involves those variables. So our pressure is 1.15 atmospheres. Our volume is 36.0 liters. We are not given moles of nitrogen gas, so that's a question at this point. We have R, it's our constant, 0.0802 or 206, excuse me, liters times atmospheres over moles times Kelvin. We're given our temperature of 26 degrees Celsius, which we can go ahead and convert to Kelvin since we have to use Kelvin for ideal gas law. And it's always good to identify your significant figures now so we don't get jumbled up within our problem. So we know we want, looking at our variables here, 3 significant figures. So at this point, looking at our information, since all variables are given to solve using ideal gas law for nitrogen, we can solve that first and find our moles. So since we're given 4 out of those 5 variables, we can go ahead and solve for N and find out our moles of nitrogen. That's going to get us one step further. So we're going to use our ideal gas law, PV equals nRT. We want to divide both sides by R and T and get N by itself. So our equation is N equals PV over RT. So we had a lot of practice using this, probably pretty used to it by now. So plugging in our numbers, we get N equals 1.15 atmospheres times our volume, 36 liters, over R, and our temperature of 299 Kelvin. We can then solve it and get our answer. So our answer is, from our calculator, is about 1.68732, and it continues from there. Looking at our significant figures, we only want 3, so we look at the 1.68. The 8 would round to 9 since it's followed by a 7. So we have 1.69 moles of nitrogen, N2. Now at this point, we can solve for our grams of NaN3. We have moles of nitrogen. We have a balanced reaction. We're looking for grams of a different chemical. So we set up our stoichiometry problem using our given. So our given at this point is going to be 1.69 moles of nitrogen. We want to convert, we're already in moles of nitrogen, so we don't want to go back to grams. That would not really help us for that one. We don't want grams of nitrogen. So first thing we want to do is get to the chemical we want. So NaN3. So we're going to go from moles of nitrogen to moles of NaN3. So it's a 3:2 ratio using our balanced reaction. Then we would want to convert from our moles of NaN3 to the grams of that chemical. And we get 1 mole and 65.21 grams of NaN3 from our periodic table. We can go ahead and calculate, so multiply across the top, divide by your 3 on the bottom, and you should get 73.4699 in our calculator. And then again, we want those 3 significant figures. So I rounded it to 73.5 grams of NaN3. So that would be our final answer for our question. So in this one, because we're given enough information about nitrogen, we use that with our ideal gas law to solve for moles, and then use those moles within the stoichiometry problem to get to the chemical we want, and then the units of that chemical that we want. So it ends up being a longer process involving kind of more steps, but it is possible because both stoichiometry and ideal gas law involve moles. So that's our connection, that's our bridge. So we're going to take a look at another example here. We're given a balanced reaction. This is a combustion reaction, so we've got our hydrocarbon, C8H18, plus oxygen giving carbon dioxide and water. So our question is, if 3,035 grams of gasoline, basically a gallon of gas, are burned, what volume of carbon dioxide is produced if it has a pressure of 0.953 atmospheres and a temperature of 35.0 degrees Celsius? So we've got a couple pieces of information here. We've got grams of our gasoline. In this question, the gasoline is the C8H18. It's also known as octane. So octane is one of the hydrocarbons that's in our gasoline that we burn. So when you hear of a high octane gas, that's C8H18. So we're given grams of that, but we're looking for a volume of carbon dioxide. And it says if it, meaning the carbon dioxide, has a pressure of 0.953 and get the temperature of 35 degrees Celsius. So we're given information about two different chemicals. So this is going to be kind of interesting approach. We're going to have to see how this breaks down, and again, if we have to do the ideal gas law first, or if we need to do our stoichiometry first to get more information and apply that ideal gas law. So we'll see how this works out on the next slide. All right, so we're going to take a look at solving example 2. Again, we want to kind of figure out all the information we're given and write that information down so we have some references. So first thing we know is we're trying to solve for liters of carbon dioxide. And we are given a couple of variables for carbon dioxide. So we're going to go ahead and record those. We're given a pressure of 0.953 atmospheres. We are not given a volume at this point of the carbon dioxide. We are also not given moles of carbon dioxide. We do have our gas constant, and then we are given a temperature of 35 degrees Celsius, which we can change to 308 Kelvin, since we need to use Kelvin for this. We can also take a look at those values that are given, and we know the lowest amount of sig figs is 3, so we can go ahead and record that. So at this point, we have 2 missing variables. So we cannot solve the ideal gas law, so we have to use our stoichiometry first. So it's really good to write down all of your variables. I cannot stress that enough, because if you can't see what you're given and see that you're missing more than one variable, then you're not going to know which step to do first. So write all your stuff down. So we're also given the 30.35 grams, or not 3,035 grams of the C8H18. Now, this is not carbon dioxide, CO2, so we cannot just convert that to moles and put it in our ideal gas law. We have to get it to moles of carbon dioxide, and this is where our stoichiometry comes in. So, can't use the ideal gas law first, we're going to use our stoichiometry first. So we're given 3,035 grams of C8H18. So we're going to first take that, we want to do the same thing we do every time, get it to moles. So the molar mass that I calculated was 114.26 grams of C8H18 to 1 mole of that octane. So we get it to moles, and then we're trying to get to that moles of carbon dioxide so we can use that ideal gas law. So we want to change from moles of the C8H18 to moles of CO2, so it's a 2 to 16 ratio. Pretty big jump there. So in this one, we can go ahead and multiply across the top, divide by the 114, and divide by the 2, and we should get 212.4978. Go ahead and check that in your calculator. Make sure you're getting the same thing and that you're putting it in your calculator correctly. Still had people on some of the finals that weren't getting correct answers because they weren't putting in their calculator right. All right, and then to round that, we want 3 sig figs, so we get, actually, sorry, in this part, we have 4 significant figures, so we can actually keep the 4th one. So we can do 212.5, and that will give us kind of an extra digit going forward to make our next part more accurate. So we have our moles of CO2, so we can go ahead now and record that in our kind of table of value or list of values here for carbon dioxide, since we have it now. And now we can actually solve for our volume of carbon dioxide, try and find our final answer, our liters of carbon dioxide. So we have enough variables now to plug into our ideal gas law, PV equals nRT. We want to divide both sides by our pressure so we can find our volume. So volume is nRT divided by P. And then we would plug everything in. So our moles times our gas constant times our temperature on the top, divide by our pressure on the bottom. And so we get, let's see, our 212, sorry, I'm doing the calculation real quick, 0.5 times our R, 0.08206 times our temperature is 308 divided by 0.953. and I got 5635.70514. So pretty big value there. And then we can go ahead and round this, and this is our final answer. So it's using the significant figures within this problem. We want to use those 3 sig figs and round this off to 5,600, and the 3 would be our last digit that we could keep. So then we'd round it to 4, make the last digit 0 so that it's still in the 5,000 range. And that would be our liters of carbon dioxide. So this one takes a little bit different approach than our first one. Our first one gave us all the information to use the ideal gas law. We solved for moles and then did our conversions. In this one, we had to do our conversions first to find the moles and then plug them into the ideal gas law. So listing your variables is so important. It gives you guidance. And be careful in the questions about which chemical belongs to that variable. And it can make a big difference in things. All right, we're going to look at one more example, kind of see the third type of problem we might encounter. So we've got a chemical reaction there. Again, it's a combustion reaction. This one has a different hydrocarbon, so CH4 methane. So it says methane is burdened in oxygen at STP. How many liters of carbon dioxide are produced or made when 6.4 moles of oxygen is reacted? So with this information, we can look at our problem, and it tells us that it's at STP. So when we see that, we know it's going to simplify our work a lot. We can just do a straight stoichiometry problem because we can use the 22.4 liters per mole to help us convert. So in this one, we're given 6.4 moles of oxygen. We want to find our liters of carbon dioxide in this. So given this, we want to start with our given value, moles of oxygen. We would convert to moles of, from moles of oxygen to moles of carbon dioxide. So that would be a, 2 moles of oxygen to 1 mole of carbon dioxide, 2-to-1 ratio. Then we would want to change from moles of oxygen to our liters of carbon dioxide. So that's where we can use the 22.4 liters. So now we just need to do our math. So we have 6.4 times 22.4 divided by 2. And I got 71.68 in my calculator, and looking at our value that's given, we have 2 sig figs, so we could round this up to 72 on this one. So we get 72 liters of carbon dioxide when 6.4 moles of oxygen is reacted with our excess methane. So that's kind of the simplest version of these type of questions you might see. Again, if you don't see STP, you cannot solve it this way. You have to use the ideal gas law. So that's looking at examples 1 and 2. Try out the practice questions now given in class, and let me know what question you have.